think the idea there for that question was that because you have resource competition, like the reason why the parallel is because you're seeing a competitive solution. That's like pretty much how I came to that answer during the exam.
No, so I mean, an outcome of having two species competing for one resource, which was the condition that we derived, is that you only have one species that persists. Given a homogeneous environment that's not temporarily variable and all that good stuff. So all the stuff that, like Armstrong and McGehee in their paper have this ginormous list of reasons why you might have multiple species coexisting on two or more resources.
So I know the last exam there weren't many questions on the readings, but then Dr. Lehman said that that was a mistake. So this exam there will be questions.
So all the questions that were not covered on the first exam, all the readings that were not covered on the first exam are going to be covered on this exam.
Are fair game. So even the ones for exam 2.
Yes.
Yeah.
Especially.
Because we know that you guys were really disappointed that they weren't in the exam.
And yeah, we know you read them really well to prepare for that.
So we want to make sure that you're rewarded for that.
Thank you.
That was decidedly a Minnesota answer. So have we put together a structure for how we're going to walk through this yet? All right. So last review session. Who was here last review session? Just sort of by awesome. So last review session we did. We essentially walked through lectures one at a time.
You mean last review session as in last week?
As in last week,
Fridays.
yeah.
Who was
Like,
here on Friday?
That's
not
a different question.
many days ago.
There's only a couple.
Yeah.
So there was like no.
So we walked through lectures and covered stuff there. And we can do that again, though probably more effective would be if you guys started shouting out specific things that you'd like us to cover. Because we go through the lectures very slowly, and it's pretty similar to what
And we can't
Dr.
do all
Lehman
of
did.
them.
So I know you guys are bristling with questions right now, so why doesn't a brave soul take one for the team and raise their hand? Yeah.
What do we need to take away from the memes lecture? Will that be testable material? What is that?
I imagine it will, yeah.
Yeah, it certainly isn't. So we're waffling on a lot of these answers.
We-
In that we don't necessarily know what's going to be in the exam. We have some small amount of influence. But
Not as much influence as last.
Yeah.
Right,
We're not
exactly.
writing. Yeah.
And so Dr. Lehman may decide that this is a really neat lecture that deserves a lot of coverage, or he may decide that it isn't. But it's certainly fair game to be on the test. And we haven't written any questions with that topic. Yeah.
Can you go for global cycles and biogeochemical dynamics 1?
One. Sure. 26.
That's a wonderfully specific question. Thank you. We just need about 35 more of those. So like, that's pretty good. I go over all of the biogeochemical cycles here. It's pretty standard.
I think it's this one.
Yeah. That doesn't count as one of your questions.
Okay, thanks.
All right.
I'll let you.
Oh, yeah. Okay. We opened this section just by pointing out how completely strange the Earth is. And you can sort of get that by comparing it to planets nearby that do not have life on them. So just from this, do you guys remember one of the points that came up for what labels Earth as weird? What number here is different from other numbers? This is a super easy one. Okay, oxygen. Why is it weird that we have a lot of oxygen in the atmosphere? Well, yes, that's why we have it. Why do other planets not have it?
It's reactive.
Super reactive, exactly. So generally speaking, oxygen at thermodynamic equilibrium should be bound up in stuff. So like in soils or in rock formations or whatever. On Earth, we have 20% oxygen in the atmosphere, which suggests something super strange is happening, that there's a lot of energy that's been put into turning oxygen into a free form that is not stable. And so this suggests a system that's out of equilibrium. And I actually ditto for nitrogen. Even though nitrogen is a very stable compound with a triple bond, it in fact is not at thermodynamic equilibrium and will tend to get sequestered in other things as time goes on. So cool, we're weird. That was sort of the starting point of this lecture. And I forget who is the Blue Planet, which is an Austrian book, so you guys probably don't know about it. But anyway, this is there's like a very romantic idea of like, aliens from space should know immediately that there's life on Earth if they just looked at the composition of our atmosphere, because it couldn't exist without a lot of energy being put into that. Do you guys want to add anything, or should we switch to the cycles and go into
So is there nitrogen, like, you said nitrogen normally would be incorporated into things, so on other planets like Venus and Mars, is it in like rocks and stuff, or?
You know, I honestly have no idea what it gets incorporated
Isn't
into.
it in like ammonia?
It's not, I mean, ammonia and nitrate are both going to be more reactive than than nitrogen gas is. I don't know what it gets built into, but certainly the planets have the same amount total as we do.
Really?
Yeah, anyone have an idea of what it actually gets put into? Who knows? Okay, this is, you shouldn't ask an ecologist rock questions. Those are difficult. The Vostok data, I guess we'll walk through this. This is fine. So one of the first pieces we went through are these climate cycles. So Earth, starting 400,000 years ago to today, has had these peaks and troughs, which correspond quite nicely both to temperature and atmospheric CO2. One of the more sobering things that comes from this is that the current concentrations of CO2 in the atmosphere correspond to times when there was no ice on Earth, such that we are currently not enormously warmer than we've been in the past, but we do have enormously more CO2 in the air. And does anyone have an idea for where that came from? So how is it that so obviously we burn stuff, it goes in the atmosphere. Where was that carbon before, and why wasn't it part of the atmosphere?
In the air. It was in the air, it's cold, wasn't it?
Okay, so one of the reasons that we have this weird unbalance is that a lot of carbon dioxide has been sequestered over hundreds of millions of years as coal deposits and petroleum deposits and who knows what else. And so by releasing that, we can essentially bring us back to CO2 concentrations that are more like when the dinosaurs were around than any time in the past 400,000 years. And this was the point, so from the cycles, Dr. Lehman brought up that we are out of temperature balance, in that these are points corresponding to the relationship between CO2 and temperature. They're very tightly coupled. And you'll notice where we are today with respect to temperature, again, isn't enormously above historical records, but where we are with respect to CO2 is. And this would indicate that as time goes on, even at our current atmospheric concentration of CO2, which is now actually closer to 480 than it is to 380, we should expect relatively enormous rises in temperature. So, exciting times.
So what's the difference between those two red dots?
Oh, this is where we are now, and this is where we would be, provided that this relationship holds. And so does anyone know why might we not have reached this temperature yet, even if we are fated to do so sometime in the future?
Because the CO2 goes so quickly.
Pardon?
Because the CO2 goes so quickly.
Exactly, so why would that mean the temperature would lag behind?
It's reflecting the sun's rays off of our ozone.
Yeah, that's sort of. So has anyone done an atmospheric chemistry course here? So I can, this is, you have to make sure that you can make stuff up before you so, does black body radiation sort of ring bells for anyone here? So, yeah, so what would happen if you took a bowling ball and shone a bright light on it, and all the energy in that light just went into the bowling ball, and none of it ever left the bowling ball? What would happen as time went on? get hotter and hotter and hotter and hotter and hotter and hotter until eventually it melted and burned a hole to the center of the Earth, whatever else happened. So objects don't just take in heat, they also emit it. And there is, so the black body radiation model is just a simplified model of heat forcing. It basically shows as you increase the rate at which heat goes into a body, you also increase the rate at which it leaves the body. And so Earth has now an energy imbalance in that we have the same amount of light coming into the system, and CO2, this is a neat point, CO2 actually doesn't really stop the amount of light that comes in. CO2 reflects, so I forget the bond angle, but the width of the angle of the spacing, the average spacing between the atoms and the molecule is precisely the right shape to reflect infrared light, but not visible light, such that the visible light from the sun comes through the atmosphere, hits the Earth, and is then re-radiated as heat. And the heat then is trapped by the CO2 and reflected back to the Earth's surface. So this is why you get the same amount of radiation in, but less radiation out. And at some point in the murky future, we'll become closer to thermodynamic equilibrium, such that the Earth's temperature is no longer warming, but it will take a long time to get there. Just because we have to actually slowly take in that extra heat balance. So it'd be as though we turned up the thermostat in the house a little bit, but we haven't actually yet reached the temperature that we set it to.
Clarence give that analogy?
I don't think so.
He loves that. He always goes over and talks about this. Think of it as a thermostat. Right now we're cranking up the thermostat, releasing CO2 in the atmosphere. There's this lag. Changing temperature happens through time.
Mm-hmm. Cool, so does that make sense? And let's burn through the rest of this pretty quickly. There's coal consumption through time. The interesting point here is that we're actually still consuming more coal than we have at any point in the past, mostly for electric production. But that might not be something that you would immediately think of if you compared our current world to like the Industrial Revolution world. Let's hang out on this guy for a bit. So what is larger here? The total output of CO2 by natural systems, or let's say non-human systems, or the total output by human systems? Natural systems by an enormous amount, right? So by this, and this is sort of out of date, but we have something like 12 petagrams per year being released by humans. If the land clearing number, yeah. Oh, so I guess here they only have 7.
Yes.
Yeah. And we have like hundreds being released by natural systems. So why should this tiny little increase of anthropogenic emissions, so human-induced emissions, lead to an increase in atmospheric CO2?
Because it knocks it out of equilibrium?
Exactly. So if you guys remember the tub model that Dr. Lehman showed, you pour in water, pour in water, pour in water, and provided that the rate at which you're pouring in the water remains constant, the tubs will eventually equalize. And so you'll have the rate at which things flow out of the place you're pouring water in should be equal to the rate at which you're pouring it in. And so the system reaches an equilibrium somewhere. But if you suddenly crank up the rate at which you pour in the water, the level rises, and we're currently out of equilibrium. In that at some point in the future, let's imagine we stuck at exactly 500 parts per, or let's imagine we stuck at exactly this rate of emissions. So non-zero, our rate is like 7 or 8 petagrams per year. Would CO2 concentrations keep going up forever, or would they at some point reach an equilibrium? They reach an equilibrium, exactly. So there's a neat paper by Kala and some of the there we go. Where they show that if we went back to roughly 1990s emission rates, CO2 concentrations would stabilize at about 500 parts per million. So that's a neat point, which I think is often not made in classes that deal with climate change, in that we could still have non-zero emissions and stabilize atmospheric CO2 concentrations. And that's just because this is a dynamic system, so some flow comes in, some flow goes out.
So right now right now we're not at equilibrium?
We're nowhere close, in that we're way above 1990s emissions and we're continuing to increase. So this was his analogy, that you're not just pouring water in faster than you were before. Every second, you're pouring it in faster and faster than the preceding second. So the system is never going to reach equilibrium if we keep doing that.
And remember that little, the kind of smallest cube represented the atmosphere. And if you just dump all the water in faster and faster, the carbon or the water level is going to go up really, really high, really, really fast. Whereas if you just pour it really, really slowly, it goes up a little bit, but then it kind of just hangs out there because it's also leaking out into the ocean.
Oh, that's true. And so a neat point
It's
from
also
that.
leaking out into the ocean.
We're nowhere close to an equilibrium with CO2 for the oceans, for example. So like if we stopped emitting completely today,
Yeah, it would take a long time for that water that's in that cup to go down all the way back to the oceans.
and we should say all of these are with enormous error bars around them. So the current understanding is that if we stopped emitting any CO2 today, concentrations of CO2 in the atmosphere would either rise or shrink, depending on where the oceans are with respect to the atmosphere. And we're not entirely sure on any of those. So there's a huge amount of uncertainty in all of these measurements and all of these flows. And I think that might be all we need to cover from this lecture. This is just industrial, pre-industrial, sinks, and temperatures. I don't think we have to talk a huge amount about temperatures. Oh, so this is a neat one. I like that. You guys know what do you call it? The triple biome boundary ecotone, where like northern deciduous forest meets prairie meets boreal forest, and that point has been sort of wandering through time, and that it's been moving west and north.
That point is defined by a precipitation and a temperature window, 2 windows. So we've tracked where those 2 windows overlap through time, and you can see that it's moving north. So those conditions are changing, so that window is moving north, which suggests that the boundary of our ecosystem is actually changing.
So has it actually been related to the boundaries of the ecosystems?
Well, the neat thing is that those haven't happened yet, and that this is a century of change, and a lot of the species are very long-lived.
Yeah.
So this reflects much more what we imagine the position of the biomes might be in 100 years, rather than where they happen to be right now. And it's also worth mentioning that a very large fraction of what we call prairie is currently corn. So that's hard to figure out where that biome is right now. Yeah, rising seas, very sad. We lose Sweden. Climate models. Macro scale, microscale. This is a nice example of a microscale model. So in a macro scale model, we have these boxes and flows, and we can now solve for equilibrium. So we just say, here are boxes, flow rates between them are defined. Let's set all these derivatives to 0 and figure out what the stocks will be. In a microscale model, we still have boxes and flows, but the system becomes way too complicated for us to solve analytically. So we can't set the derivative of all, whatever it is, 50,000 boxes that we make up for the world to 0 and then solve for the system, because that's not going to tell us anything sensible. It will tell us what the equilibrium conditions for our model will be. So what we do is we create this complicated system, and then we just simulate it in a computer without actually trying to solve any portions of it. And this can give us insights that these macro scale models, these analytical models, can't give us. And so an example of this, our weather models are like this. In that our weather models are these huge simulation things that now do a pretty good job of simulating weather 10 days in advance. The downside is that they run very slowly, and so as Dr. Lehman pointed out, the climate models that we run are much coarser than the weather models because they would take too long to run, and are therefore somewhat dubious because they can't actually predict weather. So anyway, that's a problem of microscale modeling, in that it becomes so complicated it's hard to actually simulate global dynamics realistically for long periods of time. I think let's leave it at that, the lecture. So do you guys have any questions from sort of this moment of stuff?
What's the difference? You were saying something about like you don't solve for it, but you just simulate it. So is that the difference between?
Yeah,
Like a
because you don't. So
microscale
there's
and
a lot of people will call a microscale model an individual-based model, and I guess I mean these aren't individuals; they're boxes. So it's not as though we're simulating individual molecules; we're simulating the boxes themselves. And the difference is that we make no attempt to solve the system, because at some point you have a system that's 50,000 equations all interacting with one another. And it ends up being vastly easier to put it into a computer and have the computer take little steps and figure out how all the changes happen, rather than solving all the equations.
So that's what, like where the simulation was, right?
Yeah, and so a lot of the time, we probably couldn't even solve these equations. They're probably not solvable in their current form. And so a place where this comes up, I think both of us have talked about this before, is if you're simulating a forest, for example, you could potentially make a model for each of 50,000 trees and try to solve for it. But at that point, you now have 50,000 times 50,000 equations, and it becomes much easier, rather than solving that mess, to just go ahead and actually do a simulation in a computer where you step through time in each of your equations. So you don't try to solve to figure out what the equations do at equilibrium, you rather just run the equations one step at a time. And so if you guys ever used Euler's method for calculus way back in the day, this is basically what the computer's doing. You have a function for a derivative, it's like, let's say dx dt versus x is just a quadratic function. Rather than trying to solve it, we'll just take our x value, figure out what dx dt is, and take a little step. And now we take our new x value, find dx dt, take another step, and so on. So this is just a much easier way to deal with complicated systems. And this is generally what we mean when we talk about microscale models.
What if the steps are in the wrong direction?
Pardon?
What if the steps are in the wrong direction?
That's a big problem. And so this is neat. It's one of the very first proofs in computer science that ever came up. But there is no way to prove that a computer program is correct for all instances. And so you never know that you're right. All you can do is get increasingly more evidence that your results make sense. But you can never prove it correct. All right, super exciting. Okay, next question. Other than biogeochemical stuff.
Unless you want to talk about nitrogen phosphorus.
Actually, we could do the same thing for nitrogen phosphorus cycles now. That would be super fun.
Water.
And water. You guys don't want that. We don't want that. Ask something else, please.
Can we talk about the beach hyperspheres?
Sure.
Ah.
The idea behind the niche, however you want to pronounce it.
I think it's pronounced niche.
Niche. In this case, so you could have, this is an example of hypersphere with two resources, or in this case, parameters. And if a species can exist anywhere inside this non-shaded area, but once you go to the extremes of the resource, it can't exist. But it might if you have so much of the second resource. See what I mean? But the idea is that these can expand to 3 dimensions with 3 resources, or 4 or 5 or 6. So it becomes this hypersphere. It's something that can't really be conceptualized.
So that's like adding a dimension each time. So if you were to have like 3
Resource.
parameters, then you'd have like an actual like sphere versus just like a circle. Okay.
Yes.
And the equation suggests, so in the first diagram, the 2-dimensional space, you can exist within that 2-dimensional circle. And the proportion of area from the total, so the amount that you can exist versus that total square, is pretty large. And as you add dimensions, the ratio of that area to the total kind of n-dimensional cube gets smaller and smaller. So as you add 3 dimensions, the volume of that sphere within the cube is a smaller proportion than the volume of the 2-dimensional, or the area of the 2-dimensional within the square. And so as you add dimensions, you get an increasingly small niche space relative.
It ends up kind of being like, that's where you fit, and that's about it.
Right, and it gets, and this is why, like, as the number of environmental parameters increases, the proportion of surviving space.
Makes sense.
Are we gonna have to know that those babies on the slide?
No, the idea, we would not make you compute the equations for a 16-dimensional sphere, much
they
less
have-
the ratio of that to a
I mean, they're using
16-dimensional
the word
cube.
probability, but probability is the area of that circle. Or the area over the total. So the area of the circle over the area of the square, or the area of the sphere. Not the total area.
But you should be willing to draw a 5-dimensional cube on the exam. That will probably come up.
I know, I can try for like the shadow of 4-dimensional one, then I gotta have a moving, it's complicated.
Alright,
Did you guys go over your respective STEAM lectures?
Sure can. Okay. First thing I think I did was talk about what are some of the characteristics to modern agriculture, and we have these. And this is by no means a complete list. This is just what we talked about in the class: industrialization, plant breeding, fertilizers, and irrigation. Because of these 4 things, kind of got us to where we are in modern agriculture. And then for each one, there are these ecological consequences, and they're connected. And we can solve, well, so if we think about the situation that we're in now, we're bringing a niche to one species, which is kind of backwards from how natural ecosystems operate. And we'll talk about these two. But because of this, we're increasing food production. And here we can see yields are increasing consistently from the 1960s. What's really interesting here is that we've kind of plateaued on how much fertilizer we add to every field. We're not, year after year, we're not applying any more fertilizer per unit of area. It might be increasing globally because there's more land in agriculture, but even in that one field, we're still seeing increases in yields despite the same amount of fertilizer, suggesting that we're getting more efficient with the use of that fertilizer. Talked about these consequences, fossil fuels, greenhouse gas emissions related to agriculture, water pollution, there's connections here, and how can we look for some solutions to some of these things. We can diversify cropping systems, both space and time. We talk about time in the beginning, about different options, the benefits of legumes, bringing nitrogen to our crops, perenniality, so that now we're decreasing our inputs because we don't have to do so much stuff to the field. We can also, so we're talking about diversifying in time. We can also do that in space by placing crops on a landscape so that they complement one another. We might be able to use a biofuel crop like a perennial grassland system, place that next to a cornfield where it can intercept the fertilizers that are running off, so that then it both prevents nitrogen from entering our water system, but it also fertilizes the biofuel crop. So know a little bit about the cover crops idea and crop rotations.
So did you ever decide on what is the best system?
Well, it's so difficult because of the growing conditions are so variable, even across the state. So here in Minnesota, we have this challenge of really a shorter growing season. So getting a cover crop to emerge in the fall after you harvest your corn, there's not much time before the ground freezes to do that. But now down in maybe Iowa or Missouri, you have more crop options. So there's a lot of breeding effort to get crops to either emerge earlier or are more winter tolerant. So each area has its unique challenges.
Can you re-explain the cover crop concept real quick?
Sure. So we have, if we're just thinking about a continuous corn system, in the fall we harvest the corn and usually till, and the ground is left bare throughout the winter. And you have, then at that time it's incredibly prone to erosion. That soil can be blown away, or especially after the snow falls and in the spring it starts melting. We see large losses of soil during that time, and that's where all of our nutrients are, organic matter. So to prevent that loss, I guess this is where cover crops kind of started. How can we prevent that? We can plant a crop in the fall after you harvest your main crop, so it grows up a little bit, provides some cover, and then it goes dormant in the winter. But at least there's this living cover, and it's extending that living cover in the fall, and then also in the spring it'll start growing again earlier in the spring than corn would. So again, you're limiting your soil loss. But now we're experimenting with cover crops that have other benefits as well. So they might be high in nitrogen, tissue nitrogen, so that when they die in the spring, so they go dormant in the fall, but then before you plant your primary crop, you just mow in or till in that cover crop. So then you're adding nitrogen that way instead of letting it emerge, continue to grow. I think I have a diagram of how that works here. Yeah. This is kind of how it goes. Here, this Gelfand paper is one of the readings that was associated with this lecture. It talks about the different greenhouse gas fluxes, know some of those emissions. Any other questions about this stuff? So you know the benefits of a perennial crop versus just an annual crop?
Perennials putting more biomass underground,
Yeah, that's one of the benefits
so
too.
then it's
Yeah.
like putting more nutrients into the soil.
We can see it could actually sequester carbon and store carbon down both in the roots and then add to soil organic matter. Also then, from an agronomic perspective, you don't have to go in and plant it year after year. But it still can be harvested every year.
What are some examples of the perennials?
Pardon me?
What are some examples of the perennials you've had?
Well, alfalfa is a perennial, and that's probably one of the main ones right now. Then, I talked about native perennials, so there's these grasses that we can use for bioenergy instead of eating. Yeah. And then one really cool major research program that's going on here is we're trying to develop a perennial intermediate wheatgrass. So it's a crop that could provide grain to supplement flour, so we could actually use this perennial crop for food and also fuel. But we have this trade-off. I mean, plants have kind of this trade-off where they either invest in their roots or their seeds. The roots make them perennial, seeds make them useful for us because that's what we eat or make flour out of. So trying to get a plant to invest the right amount of proportion of their energy to those two parts so that they're both, you can make money from the system, but also that it's perennial is difficult. That's what we're trying to do. questions? You want to talk about your lecture?
Sure, I'll do it on the board though.
Sounds good.
Okay.
Should bring this up at all.
So I think I put this away.
Put it up like this.
Oh, brilliant. And then you mute.
Can you mute?
Yeah. All right. And let's do that. That's it. Thanks. Cool. So can you just sort of peek at the screen on the camera quick, and what about how much of the board is in it?
That entire edge is in.
Eco.
Oh, okay, I got tons of space. Yeah. Cool. So let's start with two equations. The first, we're going to do S equals CA to Z. The second is going to be dP dt equals CP times 1 minus P minus MP. So what are these two things describing? What's this guy?
Species area.
Species area curve. Cool. So what's it describing? Rephrase the name. Species area. So what if I were to, for example, based on this equation, plot species versus area, how might this look?
Why, are you looking for like biodiversity?
No. Just how would this look?
Right. Oh, I see. Yeah, you get fewer
Yeah.
species as you keep going, or
Get it clone.
fewer increases as you keep going.
Exactly. And so as we sample more area, we find more species, but the rate at which we find them decreases. So similarly, if we took the same concept and asked what would happen if instead of area, we're tracking the amount of land that we've destroyed. So let's say we start off with this much land, and then we start paving it over for Wendy's parking lots. How would this curve look? Would we lose a lot of species originally in the first couple of, let's say by the first half? Would we have lost most of the species?
No.
No. So initial losses in area don't lead to large losses in species, whereas later losses in area do. And so from this, we actually derived a condition where we said, let's imagine D equals fraction of area destroyed. Then we can rewrite this as S equals C times, and let's say we start with 1. Let's do A minus D to the Z. From this, one other thing to take away is the island effect. And so this sort of reminded us that there's something weird going on in this system. And that's so Z for the mainland is roughly 0.2, whereas Z for islands is roughly 0.3. And so islands, you're sampling islands of sequentially larger sizes. Mainland, you do what we did in our field study, in that you're sampling increasingly large pieces of land. So first, what does it mean that there's a higher Z value in one than the other? How would that look in this figure? So like, here are 2 lines. Which one of these would have a higher Z value? The solid one or the dotted one? Exactly. This guy has a Z equals 0.3, Z equals 0.2. And you can tell that just because the Z is the thing that's increasing this function with area. So bigger Z means it increases faster. Consequently here, the dotted line also loses species faster, right? That's because the Z is telling us each unit area has more new species in it when Z is higher than when Z is lower. And so because of that, that means that we also expect to lose species faster in a system with a higher Z. That means an island system will lose more species if we remove an island than a mainland system will lose if we take away some fraction of the area. And that's just because the islands tend to have more endemic species in them, they're more different from island to island, so they have different kinds of species, all that kind of stuff. And in the lecture, this led to a question, which was, how do we deal with the way that landscapes are actually destroyed by people? Since we tend to actually isolate things. When we change a landscape, we tend to leave isolated patches of habitat left over. We're not sitting here removing concentric circles. And so that, in some ways, suggests that when we measure real systems, we may end up losing species faster than we would expect from this simple equation here. So who knows what this guy is, what this is describing?
Nothing's about a population.
Pardon? That sounded very right, whoever said it.
It's 11th metapopulation model.
Levin's metapopulation model, wonderful. Here's Levin's metapopulation model. So this is describing the rate in the relative abundance of the rate of change in the relative abundance of a species per unit time, so dp/dt, as a function of a colonization rate and a mortality rate. And so does anyone know why we have MP as the mortality rate, whereas we have CP times 1 minus P as the colonization chunk? What's MP, shall I ask? So M is per capita mortality rate, and we multiply that by the population size. So that's giving us the population mortality rate. So why don't we just compare that to CP in this model? You're going to go draw the grid?
Because I can't understand this without the grid. So this model, dp/dt.
This is the more user-friendly version.
P represents the proportion of boxes that the species has. dp/dt is a change over time. So that can mean that there are either more boxes or fewer boxes. And the input of those boxes, so what's, if a species dies, we take away boxes. And if a species, how does a species increase its boxes? Through colonization, right? So mortality, we can have all of them die, we can have one of them die, but what's limiting colonization?
Boxes that are already occupied.
Right, the boxes that are already occupied. So why we have to do, so CP is gonna be the number of new, boxes, but as we fill more boxes, there are fewer boxes left to fill. So any number of them can die, but for colonization, you're limited by boxes that are empty.
Yeah, and since P is the fraction of sites that are occupied, 1 minus P is the probability that a randomly chosen site isn't occupied. And so for a randomly dispersing organism, it shows us the probability that a new propagule will land at a site where it can survive.
And remember that P in this case is a fraction. So if P is 0.25, that means about 1/4 of this grid is occupied by a species. And 1 minus P means there's 0.75 empty boxes left over.
And so this is actually a good example of the macro-scale, micro-scale approach, in that the equation has this sort of nebulous fraction term in it, which allows us to do a macro-scale, an analytical approach to this. We don't actually have any spatial terms in here, but we're implicitly including space as the fraction of sites that aren't occupied. On the other hand, if we were to write a computer program that actually filled up boxes and had boxes die and all of that stuff, this would now be a micro-scale approach to the same equation. And so we use this sort of weird equation because it's a great approximation of a system that we would usually have to simulate. Although as soon as the system becomes more complicated, like we add explicit dispersal distances rather than letting the species disperse randomly, then we actually have to move into a simulation framework, as it becomes much harder to do that using analytical equations. Cool, so does the structure of this model make some sense for why we've put it together like that? So how would we go ahead and figure out the population size at equilibrium? Huh?
Set it equal to 0.
Set it equal to 0. So when we set this equal to 0, we're saying what's going on when the per capita, when the change in population size is 0. So that means when the population is no longer changing in size, or is at equilibrium. And we can now solve for P star. So P star being the equilibrium population size, times 1 minus P star minus M P star. So what can we do first to this? Divide by P. And what do we have to do as we're dividing by P? What's something divided by 0? It doesn't exist. So we have to promise at this point that P star is not equal to 0 because we can't solve for those conditions anymore. We've assumed by dividing by 0 or dividing by P star that P star isn't equal to 0. So you don't have to show that when you're doing proofs or writing about this in the test should this come up. But just you should keep this in mind if you're ever trying to do something like this yourself. And you can tell one of the reasons this is important is what do you get here if P is 0? It works, right? Yeah. And so that actually won't be the case when we've solved for the system. So here we now have 0 equals C times 1 minus P star minus M. So now we can bring the M across. M equals C times 1 minus P star. Oof. And now we can divide by C, which gives us M over C equals 1 minus P star. And finally we can solve P star equals 1 minus M over C. And you'll notice now P star equals 0 doesn't work. So we have to keep that in mind separately. But cool, so this now describes the fraction of sites that are occupied at equilibrium. And so an interesting question with this is, what would have to happen for this species to occupy all sites? 100% of sites. Right, so how would we get that? So let's get rid of the proof and just look at the equilibrium population size. So we're saying P star equals 1 minus M over C. So you guys are saying this term has to equal 0. How would we do that? Two ways.
Mortality.
MS.
Yeah, mortality could be 0, or colonization rate could be infinity. Which means for this population to fill all sites, it would either have to be immortal or infinitely fecund. And we know both of those things are impossible. So this tells us implicitly that this species in a metapopulation framework like this, so an Apache world, can never occupy all sites, no matter how good it is at dispersing and how persistent it is in sites. One last part. So you saw how we added habitat destruction to that model. How would we add it to this model? Here, what does the 1 represent?
The entire.
100% of sites, right? So how would we add a destruction term here? 1 minus D. So given some habitat destruction, P star equals 1 minus D. 1 minus D minus M over C. And you remember from the slides that we showed a species that was able to persist under these circumstances may not be able to persist after a destruction event. And so what would we call, and so just the last piece to take from this, you guys remember the reading on habitat destruction. When would we expect a species to go extinct? Immediately after a habitat destruction event takes place, or after a while?
After a while.
Okay, and what do we call that effect? Extinction debt. So that means you have a species that has now a negative growth rate. And so even though all the individuals weren't killed by the habitat destruction event, it's not as though the bulldozer ran over all of them, the species is still slated to go extinct in the future because there's no longer enough area to maintain a population. And so the last piece from that, do you guys remember, is it the good dispersers or the good competitors who go extinct in that paper? It's the good competitors. And so in this particular model, they assume a trade-off They assume that species that are good colonizers are bad competitors. So they sort of have this trade-off with species that are very good competitors disperse slowly. And within their model, they actually show that the most abundant species, the best competitors, are the ones that go extinct following an extinction event, following a destruction event, which is kind of cool. So the most abundant species are the ones that disappear, rather than what you might think, which would be that the rare ones disappear. And that is completely an outcome of this trade-off. So if that trade-off were not there, you could end up with a different outcome in that model. Do you guys have any questions left on this stuff? Going once.
So the rare species don't go extinct because they,
It's just an outcome of this assumption here.
yeah.
And you can actually, so why do you think good dispersers, why would they be less affected by a habitat destruction event?
Because there's no more area to disperse into.
Well, so we've destroyed area.
Yeah.
What will the dispersers do in response to losing some of their area?
Go to other areas.
They keep dispersing anyway, so they're able to move around. The good competitors, who we implicitly are saying, we're saying by assumption that they're bad dispersers, aren't able to go to new sites because they're so bad at dispersing. So it's imagine you only make 2 seeds per year, and now both of them end up landing in a destroyed area, population goes extinct. Whereas if you make 10 billion seeds per year, you only need a couple of them to get to the right place in order for your population to persist.
And competitive ability in this case refers to like if the 2 species, kind of like an R-star situation with a limiting resource, or if the 2 species were in the same habitat, one would outcompete the other. That's that measure of competition, but that's on a very local kind of per patch in this meta population scale. So someone who's going to win in a patch is not going to necessarily win in the meta population.
So are you saying someone who like wins in a patch has less species per year?
Pardon?
Did you say that so someone who wins in a patch produces less species and it makes
Produces fewer offspring, yeah.
Yep.
Exactly. And that's just the assumption of this one version of the model. And there are literally dozens of other models that assume different trade-offs between like mortality risk and competitive ability. And so
And
this is,
defense
and what?
there's like a bunch of other ways that you can trade off with competitive ability, but this paper just focuses on this one specific trade-off.
Yeah. And so should it come up on the test, perchance, it would be worth keeping in mind that not all models that follow the Levin's form require this trade-off, and that if the trade-off is different, you might get different outcomes for who goes extinct when.
So you should think of that trade-off as being like, the more specialized a species is for a niche, the more susceptible it is to changes to its niche?
Well, so actually, the more, yes, although I'd actually say that's not necessarily the way I would think about this, because this is a very particular trade-off, and it actually goes back to what you were saying just a moment ago, which is if you're in a plant, you can grow roots or you can grow seeds, but you can't grow enormous quantities of both. As in, like, the plant has to put some amount of energy into leaves, some amount into roots, and some amount into seeds. And this model assumes that the ones that put a lot of energy into the roots become good competitors, but bad dispersers because they have fewer seeds. Whereas the ones that put a lot of energy into the seeds put less energy into the roots. And so it is technically true that it's so essentially there's a more specialized niche, but that niche is this emergent property of a lot of complicated interactions. So I'd say it's simpler to just think about the seed
And
versus
I would
root
avoid the
trade-off.
term niche in this case because we're not talking about really environmental parameters at all.
Right, the niche now, like your niche axis is like a vague spatial
Yeah.
amount that you can fill up under different circumstances. So you could plot it and you could write an equation, but it's maybe not so intuitive.
It's less specialization and more you have a finite amount of energy and you need to put it into different places, but that doesn't necessarily equate to specialization.
Like I like to think of this as a really like old school computer game where you can like give your character like mage points or I don't know what luck points. There we go. And so the plants all get a certain number of chits, and they put some of their chits into seeds and some into roots. And they now have to sort of play off of that strategy.
How do invasive plants disperse their genes?
We disperse it for them. Yeah, you get a little level up there. So invasives are a very interesting piece. We could talk a lot about that, but they're not going to be on the test, I think. I don't want to promise that. They might be on the test.
Wait,
Shouldn't
just,
be.
what was that you brought up?
I was just trying to extend it a little bit further and wondering how invasive species fit into this framework. Because they're kind of good at both, or do we help them?
Or,
So one of the theories for why invasive species are successful is that for some reason or another they end up with more, I don't want to say more fitness, but they can essentially end up having both bigger roots and more seeds. And there are a lot of theories for why that is. Some of the more popular ones are that they've escaped natural predators and diseases, such that they now have more energy than everybody else does. So they can essentially invest more in everything. And what does ecology tell us about things that are better at everything than their competitors? They wipe them out. So what do you need in order to have coexistence? Limit yourself more than you limit your competitors. Is sort of you should say that 10 times each night before going to bed. That's the nub of ecology that you should carry with you, and it will get you through most questions on the test if you follow it through.
and that's for coexistence.
Mm-hmm. That's coexistence.
Have we covered invasive species at all?
No, I don't think so.
I was just curious.
Maybe anecdotally, but not sufficiently that it's going to be a piece of the test. Next time.
Okay.
Oh, did you have a question?
See, I don't know if I would cover invasive species in an ecology class. Because all the principles of basic ecology, you can apply to the characteristics of a plant and judge the outcome of competition between that plant. Whether that plant is from there or not, I don't think that matters as much as the dynamics.
It's a breakdown of the classical models of ecology. We're not entirely sure why. Other questions, or should we move on to a new topic? 3, 2, 1. New topic. All right. I'm going to turn this guy back on.
Did you guys see the review session from last Friday too, or is it just today?
Just today. And with any luck, this one will even be viewable on YouTube, which I don't know the last one was.
I think I watched it on YouTube.
Oh, it worked.
Yeah.
Okay, that's great. Yeah. So I think we get 100,000 followers or more, we start getting some fraction of the proceeds from YouTube. So that might.
Your friends.
Yeah, rally guys.
All right. I think it did stuff. All right, so other topics you guys want to cover for the next, how long do we have? We have another 25-ish minutes. Right?
Yeah, I got a part of that one.
All right, next.
Should we talk about measures of biodiversity? If somebody asks anything. So how can we measure biodiversity? That I put down the screen. What's species richness?
Number of species represented in the system.
Okay, so
So then the second measure of biodiversity we have up there is Shannon diversity. And how is that different than species richness? What does it take into account that just counting the number of species in a unit of area does not?
The prevalence of the species throughout.
Right, so the species abundance. So there's two examples. Think of a community of 4 species, and if you have a community,
Oh, it's upside down. Yeah.
whoa, that's backwards.
Don't we push the paper off?
Where's the, this is the review, hold on. Can we go back to the
We
lecture?
take
for
the
this?
controls of the airplane and flip them off.
What lecture is this? This is lecture
19.
19. So to measure biodiversity, say you had a community of 4 species. And here we can see that the proportion of these species, you've got one species that's 0.4, one is 0.3, one is 0.2, and 0.1. And you might compare that to a community where there is a disproportionate amount of species 1. So the species richness of both of these communities is 4, right? Because there's 4 species in each one. However, the Shannon diversity takes into account the proportion of the number of individuals in that community. And if you calculate the Shannon diversity index, you can see that it's a lot higher for this community than it is for this community. So this community we can characterize as perhaps more even than this community. And the effective number of species is just putting the Shannon diversity index, or putting 10 to the power of the Shannon diversity index, which says the effective number of species. So this community is driven pretty much by 2 species here, because these are in such low abundance. Whereas here, it's driven by, or it's made up of about 3.5 or closer to 4.
I think there's an example where they're equally
And
abundant.
yep, there's an all. So then if you look at a community where here the species richness is 4 and the effective number of species is 4 also, because they're each equally distributed.
Is one measure better than the other, per se?
For richness versus
Shannon
Shannon.
diversity?
So it depends entirely on what you want to figure out about the system. In that richness is telling you the number of species that are present, and Shannon diversity is giving you some sort of measurement of the prevalence of common species is basically what it's telling you. And both are useful for their own reasons. So like if you're trying to figure out how many dominant species are there in a system, Shannon diversity is a great measurement. If you're trying to figure out how many species exist in total in the United States, then you want to use species richness.
You'll probably come across other things too, like evenness, the Simpsons index. Those are all related, but different equations.
They're all part of the number series.
Yeah.
Okay.
So you please remember what the equations are for these?
Pardon? That's the equation.
We need to remember it like off the top of our heads.
Oh, that one's not bad.
No, it's not. I remember.
Okay.
I know that one. I don't know if it's gonna be on the test, but like that's important for your like upbringing as a well-educated human being. This is like best cocktail party trick ever, because this allows you, if you do this as log-base 2, you can calculate the entropy of a system, so the amount of information that's required to efficiently encode it. And that's like super cool, because imagine like some cute person comes up to you at a cocktail party and you're like, hey, I can derive the entropy of our pay bill, whatever, I don't know, something or other. And then they'll think you're really cool. And,
Has that worked for you?
yeah, I get a lot of drinks bought for me. I don't know, get it to go away, I guess. Anyway, no, so this is actually useful in more places than you might think, and it's pretty easy. So I'd say learn it and love it.
So the main way that biodiversity is measured is by number of species.
And that's actually quite contentious these days, because like you do get papers that say that the number of species in a system is clearly related to the biomass of the system, And like they're counting 6 or 7 species that are like one little pathetic leaflet sticking up out of the ground. And it's really hard to imagine that like something that is 1/1,000,000,000th of the mass.
Also
of the system
depends
is
on,
affecting it.
like, yeah, it depends on how you're measuring the system as well.
Yeah, but I suppose species richness always has its place in that a room with a little bit of Ebola in it is very different from a room with no Ebola in it. So number of species does matter from time to time.
In an applied sense, sometimes it's a lot easier to go out and count the number of species in an area rather than to try to estimate how many are there and then have somebody come after you the next year and try to do the same thing where their idea
You know, and one of the bigger ones as well is like experiments. It's very hard to maintain a certain evenness because you have to like go out and selectively weed and add individuals.
Yeah.
Whereas it's pretty easy to at least plant some number of species and let them do their thing.
So it's supposed to be.
Yeah. Anything else?
So is Shannon, so is the Shannon value only applicable to number of individuals, or has been used to like calculate like biomass per species, like that kind of thing?
So notice that it's the P, the proportion of individuals. So they will use cover too, biomass or percent cover.
Or
Okay.
percent biomass or proportion.
Okay, so it's just a proportion.
Yeah. Yes, sir.
So, is that index kind of weird because it'll count like a pig and a tree will give the same amount of diversity as like 2 very related endomycorrhizal fungi? You know what I mean?
It doesn't take into account like the
Yeah.
phylogenetic component.
So, is that like a problem in
Yeah.
biology?
Well, I suppose phylogenetics is pretty bunk. So, like evolution is a weird idea.
There's a whole discipline.
There is a large world.
that
So,
explores.
yeah, where this comes from is there's this idea of phylogenetic niche conservatism. So things that are more closely related should be more like each other. The problem is that that is not always the case. So,
There's no like happy trend or trade-off that we can draw about phylogenetic diversity yet. And people are still kind of hashing out under what conditions more related individuals are more similar or are. And same with genetic diversity.
what should we pull up the syllabus one last
I
time?
want to talk about the conservation biology lecture, Leopold and Schweitzer.
Do you want to talk?
No.
Would anybody like us to talk about conservation biology and Leopold and trees?
Okay, good.
Enthusiasm is overwhelming.
Why do you want that?
Huh?
Oh, it's
Just because it's
It's
not,
like
it's not like
philosophy.
equations and stuff.
It's hard.
it's not science.
They're for
Which is whole point.
Right. No, that's,
Yeah.
I'm in the conservation biology grad.
Right.
It's just more difficult.
Yeah.
You guys ready to save the planet in your career?
Who's ready to go work for Exxon? Okay, anything, so this is like our potential smorgasbord of things to talk about. So that's like that junk from there down.
So no old material?
Huh?
So no material before that?
There'll be, yes, there'll also be
I mean,
material
to
before that.
look at here.
You
Oh,
can
we
ask whatever.
could cover stuff before that if you'd like.
Break some of that again, is that
50-50. Yes, sir.
I know you guys said you didn't want to, can we finish up biogeochemical cycles?
Like the nitrogen and phosphorus and stuff? Sure.
What lecture?
Phosphorus cycle's long. Water cycle's connected to everything. And nitrogen cycle, we modified it.
We've modified it.
Here.
Let's December 3rd.
Might not.
So the test is this Wednesday, what time does it start?
9:30.
9:30 minutes here.
And we can,
And, yeah,
I can take first.
yeah, so do that.
Because I
You can
saw,
wait.
so I saw AB's practice. So.
oh, I think
It's
probably
it's
done.
really at 10:30, but
Start-
then we can start it early, is
Yes,
the
we
idea.
can start at
Go
9:30.
until
So
1:20.
someone will be here.
Someone will be here
At
from
9:30.
9:30 until 1:20.
Yes, someone will.
But it's only supposed to take like an hour, right?
Well, I have to.
It's supposed to
I have
take an
grade
hour and a
paper.
half.
You know, I
But
just
it could
have
take
like
as
90
long as you
minutes.
want to know.
Yeah, but we're gonna be a lot saltier by 1:30 than by 9:30. So
Yeah.
pick your times.
Oh,
carefully.
yeah, you're all here earlier, you'll get better responses.
Cool, okay, so I mean, we can walk through this. We did the carbon cycle. Did we actually, yeah, nitrogen cycle. So how has the rate of nitrogen fixation changed in the last 100 years?
Doubled it?
Hmm?
Have we doubled it? Or
Doubled it,
okay,
exactly.
got it.
All right, why did we double it? Whose fault is it?
Americans?
The
Is it?
Germans. Stupid Germans.
Bosch.
Yes. Fritz Haber invented a way to fix nitrogen from the air using natural gas and magic. And it turns into ammonium, and then we can use it for fertilizer or for bombs. And he's a neat guy, and so just looking into his history, he has all kinds of skeletons in his closet. But the outcome of this was that all of a sudden we could make essentially free nitrogen, which before had been a huge limitation on the carrying capacity of people, and that we were like fighting wars for islands of bird poo, so that we could take the bird poo and use it as fertilizer.
Oh,
And now all of a sudden you could pull it out of the air.
Essentially.
And I forget, so actually the articles at the time praised it as like bread from air. It was a big sort of new world thing. Consequence of that is that the world now is full of a lot more nitrogen than used to be the case. That can lead to loss of species because you reduce trade-offs in the world. So you essentially get rid of one of the axes in niche space because now there's an enormous amount of nitrogen. And you can start shedding species as a consequence of that.
We didn't talk about that.
We didn't talk about that. Forget
Just
what I
wanna
just
make
said.
sure.
Forget about that.
It's
part.
interesting. It's interesting.
As you reduce one of the parameters, like
It's-
on the hypersphere.
It's-
Yes.
that was words that shouldn't have been. That's contentious, I should say.
Is that like a model though?
Yeah, so I mean, you can model it either way. It can either lead to increased or decreased diversity. Phosphorus cycle, yeah, is terrible and awful. And I don't think we're going to talk about it.
Yeah, it cycles really slowly, and most of it is in rocks now. We're mining those rocks and running out, and we can now see in the foreseeable future like peak phosphorus and peak oil. So it's going to become more expensive. There'll probably be war spot over it until we can figure something out how to recycle it.
But don't worry, that's not happening yet.
Right.
It's okay.
It's the attitude.
And just the reason the phosphorus cycle is complicated is that phosphorus can take on all kinds of really wacky forms, some of which are mobile in groundwater and some of which aren't, and some of which are biologically available and some of which aren't. So it's really just a terrible element to work with. And so this is a very kindly, simplified figure of stuff going from rock to ocean. But there's a lot of crazy stuff that happens in the ground, which is why we're a little bit afraid of it. And then water cycle is even stranger because there's an enormous amount of water. And so I don't know, I actually wasn't here for this. Did we talk about it as an energy cycle or not?
It was kind of, he didn't get to allocate as much time as he wanted to the water cycle, so it was just kind of rushed through.
All right. I don't think it's going to be covered in the exam, probably not. All right. Watch the Magic School Bus episode. All set.
So with phosphorus, why would it just be for fertilizers that
Yeah.
like humans would be interested in it?
Yeah, so where do we have phosphorus?
Well,
DNA and also having ATP. So we care enormously about it in terms of growing food. And so like, does anyone know the sort of stereotypical 3 fertilizers that we add? So nitrogen, phosphorus, potassium. Exactly. And so it's just one of the things that makes plants grow better under most conditions. All right, you guys have 5 whole minutes to throw us whatever last curveball you have. Or we could have like a 5-minute standing ovation.
Wait, so is potassium pretty much unlimited then?
No, you just need less of it.
Okay.
By an enormous amount. So I think like 2 orders of magnitude less than you need of nitrogen. So it matters, but it is
We're not making wars
sufficiently,
over it.
it can be used in sufficiently small quantities that we're not really running out of it. A moment of wisdom, anything? Yeah.
So, one thing that's bothered me for a while is modeling a herd population.
Pardon?
Modeling a herd population.
Herd population, yeah.
What method would be most useful for that? And
Based
because
on
I don't really.
graded assignments, which would you imagine was the case?
I really don't.
Or
know.
which would you imagine we thought was the case? So you have a herd. So remember, let's simplify down to logistic growth and a Leslie matrix. So what can a Leslie matrix do that we don't do in logistic growth?
Age classes?
Age classes. What can logistic growth do that Leslie matrices don't do? Carrying capacity. So Leslie matrix has exponential growth. It has no carrying capacity built into it. It's just exponential growth in different age classes. So if you're growing a bison herd, and you're feeding it, and you're able to give it pasture, or you can increase or decrease the amount of land available to it, and you're harvesting it at some rate, what do you think is going to be a bigger limitation in your modeling framework? Is it going to be carrying capacity, or is it going to be age structure?
Age.
And that's the reason that we had as the answer in the midterm that it was Leslie matrices, is that the age structure matters enormously for something like a bison, because in the logistic growth model, you're assuming the moment a bison is born, it starts having its own babies, which is not particularly realistic. You also assume that fecundity and probability of mortality are constant through time. So each fraction of a bison has the same probability of reproducing as each other fraction of a bison, and it has the same probability of dying as each other fraction of bison, which is manifestly not true in big complicated vertebrates. So both models have their limitations, but under any interpretation that we were able to think of, the Leslie matrix gives the problems with that model are less important than the problems with the logistic growth model. Can we give an example, pardon, of where the logistic growth model would be used?
Would be better than the Leslie.
The lemna.
Longer.
Yeah, so anything bacteria.
Lemna or humans.
That don't have
or
age,
both.
I mean, bacteria don't really have age classes.
And so
they
the
could
reason,
reproduce at any time.
And if you were modeling bison across the entire North American continent, you might also choose the logistic growth model instead, because there the carrying capacity probably becomes quite important, and you care less about how many individuals are being born at each moment in time. So you're happy to average across individuals, whereas for your herd of 8 bison, you probably care a lot about whether half of the population is reproductive or not.
So like the scaling and the reproduction rate?
Yeah, so it's not just the scale and the rate, but so like humans, you could model as a Leslie matrix. If you have 10 humans and you want to figure out how many humans will be there in 5 years, and you're a terrible person, you could model them with a Leslie matrix. But if you're trying to project the growth of world population, that's not going to work so well. And you can see we're approaching carrying capacity, so the Leslie matrix wouldn't give us a very good indication of that. All right? Good luck on the test. Contact us with any further questions you have. Please don't ask questions if you're in my section, I'm posting preliminary grades on papers right now.
Yes.
They're not final grades. We're gonna meet and have like a great secret smoky room
Yeah, so if
discussion
the grade
about
comes up
them.
for your paper, it may not be the final thing.
So please don't email me about the grade until the end of the week when it will be finalized.
Well, we know our, like, grade out of 200 for the lab portion before the test.
Well, you have most of it.
Yeah, you'll have
Yeah.
all of it there, but like he said, the paper grade might be adjusted so that we're all on the same scale.
So the paper grade is certainly going to be within 10% of whatever it is right now.
Everything else should be there.
Alright, you know, like participation and stuff, like.
Well, I think, yeah,
So if any of you guys know, I've invested some time into trying to figure out the clicker scores, but apparently they don't get reported to us until the end of the class. And so all we're told is for each of you whether or not you answered more than 70% of clicker questions. And so we'll send out the participation scores when they come. We still have no real idea of how that's going to get integrated.
Yeah, so you don't know like what percentage of the total.
Apparently they're not willing to tell us that, however it's been set up. This is
Well,
too...
shouldn't it be something that should be in the syllabus at the beginning of the semester so we know?
Pardon?
Well, it says 200 points for midterms, 200 points for lab, 100 points for final.
What part?
So,
Sorry,
yes.
what should be in the syllabus though?
Well, so shouldn't the points like that we're gonna get from this be in the syllabus?
Oh, they are. So that's that's the participation points section, which I think is 70 points.
Oh, maybe a little like
Yeah.
stats.
So that is written into the syllabus.
Okay.
We just don't quite know how much of that we're going to allocate to clicker questions versus other stuff. And that's just because we have no conception of what fraction of the class has passed the 70% barrier. So if it's like 10 of you, we're going to have to rethink how we grade participation. But if it's 95% of people, then we'll probably use that as the main component.
And then the main component, so lab.
So no, if you look at the syllabus, you notice most of the grades are from actual assignments. And you can see what the grades are. A small fraction of the grade is just participation. That's the only way to look at it. And it's a relatively small fraction.
If I grade all the papers and they turn out to be like 5
It's
in
probably
the Adam section,
from like
I might
one
scale
letter.
down or scale up or whatever. So that's the only reason why
Just like I
change. And if I just like, as I read more papers and I'm like, oh, I
Whatever, so
forgot
again,
off
we'll
for
try
this
to find
percent,
out.
this thing, but not this percentage. I only know that once I read
And if
it.
you-
So I would say it's unlikely that it would change by more than 2 or 3 points, Yeah.
Well, no, so we'll send it out whenever we end up doing it. And you
It was probably because you put less, like you would have gotten 2 with a 4-point question.
Yeah.
You would have gotten 2 points for lesson matrix, and then you probably didn't give a satisfactory.
Okay, so probably didn't say why.
Yeah, probably, yeah, exactly.
More significant. Yeah, so I was just wondering if I got it all around.
Right, no. We divided it into 2 points.
So I was very not sure of that.
Yeah,
Because
yeah.
No, so.
So you guys can see like just.
We have,
Yeah.
we have, the first year one, that's not the same.
Okay.
This will be.
So everything sets the first.
Everything, that's the first one. Everything is all the second.
so I guess probably because that's the
just about done with
the
your
answer
section.
then. I wasn't sure
And
if
so,
I
sorry, there's some debate between some students whether it's 100 points for each midterm, 200 points for lab, and 100 points for the final.
Yeah, I guess you just can't define it.
So you're gonna get syllabus is the point sheet.
But
Points are not
then
the
the final
section,
process.
and then.
Well,
Syllabus is 100 points for the final. So
Yeah,
it's 200.
so-
We're gonna, I think it's
Is this all around?
which, that's one of the